Neural networks have become common in our modern world. They are a powerful tool that has been providing many benefits to us. They do things like filtering spam, voice recognition, and some are even being developed for driving cars, among many other things that they do. Despite the sophisticated things that they can do, they're still accessible to many of you. You can learn to build your own neural networks. What you need as a background is relatively simple. You should know some algebra, and it's best to have some experience programming. Most of the popular frameworks for building neural networks use Python as the language. Knowing algebra helps, but it's not absolutely necessary. But it does make it easier to understand. In any case, if you don't have a strong foundation in algebra, follow along anyway. This presentation is meant to be accessible to most anyone. Here's what you will learn in this presentation. You won't learn enough to be able to build a neural network yourself just yet. You'll have to go on to some further study to be able to do that, but you will learn the fundamentals of how neural networks work, how they're built, and how they make their calculations. And part of the path that we will follow to get there is to review a little bit of real neuron behavior and use that as motivation for design of artificial neural networks. And despite the fact that we use a relatively simple model, artificial neural networks still exhibit remarkable performance. Here is a schematic drawing of a real neuron. It consists of several things. Dendrites, which bring in signals from other neurons. A soma, which is the main cell body, which is where the signals accumulate and add up. And then an axon, which transmits calculated signal, further to new neurons. When the signals accumulate in the soma, if they reach a high enough threshold, they will trigger a spike signal, a pulse that travels down the axon and is transmitted to other neurons. This image shows real neurons in a network connected together. So what kind of signal might these neurons transmit? As mentioned, they do send a spike, essentially a pulse that travels down the axon to other neurons. But other research has shown that with more stimulation, neurons spike more frequently. And this suggests that it may actually be the spike frequency, which is kind of an analog value rather than a spike itself, kind of a digital value that's being transmitted. Again, the more activation a neuron gets, the more frequently it spikes, and it's possible that that is the true signal, the spike frequency that is transmitted. So if neurons do output a spike frequency, what might that output look like? Well, we can imagine that if a neuron is not very stimulated, that it would not output very much. We can also imagine that if it's getting more medium or moderate stimulation, that it might finally respond and send out some spike signal in sort of a linear fashion. And if it is heavily stimulated, it may actually saturate and not output much more for additional input. And the net result would be this sigmoid shape. So we've talked a little bit about how neurons and neural networks process information. How might they encode learning and memory? Well, in 1949, Donald O. Hebb, in his book The Organization of Behavior, suggested a model for how neurons and networks do that. His model of learning suggested that use strengthens connections between neurons. This is sometimes described as neurons that fired together, wired together. And this is known as Hebbian learning. So the takeaway from this is Mr. Hebb was proposing that it is the pattern of connection strengths that encode learning and memory in real neurons and networks. So we have discussed a number of models about how real neurons behave. Understand that further research has indicated that neuron behavior can be a bit more complicated than this. Nevertheless, these simple models are an accurate reflection of some of neuron and neural network behavior. And we will see that even with these simple models, artificial neural networks can exhibit some quite remarkable behavior. So inspired by our understanding of real neurons, here is our artificial neuron. Like the dendrites on a real neuron, there are multiple signals coming in from multiple other neurons coming in through multiple inputs. And the connection strength between those connections is expressed in these weights, these W's. These weights express the connection strength between this neuron and other upstream neurons. And the way that is expressed is multiplying the signal times the weight. Then all of these weighted signals are added up, and then finally an additional signal called bias is added, and the bias is a reflection of how activated the neuron is on its own without any other incoming inputs. Could be this neuron is already highly activated, or could be suppressed, and that's reflected in the bias. Once all these weighted inputs and the bias are added together, that signal is then processed through the activation function. Now, we previously mentioned and tried to motivate choice of a sigmoid-shaped function, and that's what we show here. Be aware that other kinds of activation functions, other shapes can be chosen, but the sigmoid is most easily motivated from a biological standpoint. Here's how we express that mathematically. For each input, multiply the input times the weight. Add all of these weighted inputs together and add the bias, and that gives the activation of the neuron. Once we've added together all the weighted inputs and added the bias, run that through the activation function, and that gives the neuron's final output. So that's it. That's our artificial neuron. It's really a fairly simple object. Multiply weight times each input, add all of these weighted inputs together, add in the bias as well, and then run all of that through the activation function to give final output for the neuron. This object was first introduced in a 1943 paper by Warren McCullough and Walter Pitts, and it was later called the Perceptron by Frank Rosenblatt in 1962. Note that these earlier descriptions of this artificial neuron had a step activation function, perhaps more like the spike output that we described earlier for real neurons, rather than the sigmoid output that we are describing here. Here are these relatively simple objects integrated together into a multi-layer artificial neural network. This is sometimes known as a multi-layer perceptron. Notice that this is what's called a fully connected network. That is, for every neuron in a layer, that neuron connects to every other neuron in the next layer, and so on. So signals are introduced at the input, say for example, a picture of a cat or a dog. The signals pass through the network, getting processed by the neural calculations as they go along the way, and then finally the output indicates what the neuron, how the network categorizes that image. For example, indicating that this is a dog. Much of artificial intelligence entailed using traditional programming languages to program intelligent behavior. It involved writing sets of rules that were intended to reflect intelligent behavior. This was quite successful for some things, such as computer programs that could play checkers or chess, but that approach struggled mightily with something like image recognition, something which is easy for even a young child to do, to recognize what an image represents. Recall we indicated that connection strengths between the various neurons encode the learning and the memory in the network. So how does one program those connection weights? How does one program a neural network to do, say, image classification? Let's explore this question by examining a slightly easier problem of recognizing handwritten digits. This is the MNIST handwritten digit database, or these are example digits, handwritten digits from that database. How would we go about writing instructions, writing rules for recognizing these numbers? For example, look at the number 7. How would one write rules to recognize the number 7? You could describe it as a horizontal line near the top and a diagonal vertical line below it. Some of these numbers vary. This has a horizontal line at the top and a less steep, more diagonal line underneath, so there's some variation here. Would you specify coordinates indicating where a 7 could be found? That would probably not be a best choice. I mean, for example, someone might write the 7 off in the corner of this box rather than centrally located like is in many cases. Also, there, as mentioned, there's quite some variation of these 7s. This 7 has a dash going right through the middle of it. So the rules that would be needed to recognize even just a number 7 can be quite complicated, and there can be many of them. All those complicated rules are for a relatively simple problem. What about the more complicated problem of categorizing images as cat or dog? Of course, you have to contend with the numerous varieties of cats and dogs that exist. In addition to that, how does one describe what a cat or a dog looks like? Where would one even begin to do that? Even if that were possible, you still have to contend with all the different varieties of images. Dogs running, dogs sitting, dogs looking at you, dogs looking away, dogs during the day, dogs at night. The number of the kinds of variety of images that could exist is enormous, and the number of rules would be astronomical. So clearly, traditional artificial intelligence, rules-based AI, is not the right approach. Instead of working with written rules, however, we can take advantage with neural networks where they can train by example. So we can provide all sorts of examples of dogs and all sorts of examples of cats, and as the network is getting trained, it would get wrong answers, and we can correct the network so that it gets the right answers. Recall that, as we mentioned, the learning is encoded in the connection weights between the various neurons, the connection strengths between the various neurons. So how do we adjust those? Well, computer scientists have figured out algorithms that make those weight adjustments based on the errors made by the network. So when the network gets an error, gets a categorization wrong, gets the answer wrong, the network adjusts the weights and biases to get the network's output closer to the correct answer for one layer. Once it's improved for that layer, the network can go to the previous layer and improve and adjust its weights and biases to get that layer closer to the correct answer. And once that is improved, it can go back to the prior layer and improve its weights and biases to get the network closer to the correct answer. And so on and so forth, back to the beginning of the network. So the programmer does not program weights and biases. Instead, the network figures it out on its own based on examples. This is part of the magic of neural networks. It is astounding that networks of these relatively simple objects can achieve such remarkable human-like performance. The ability to recognize objects, the ability to do voice recognition, being able to learn from experience, even being developed to be able to drive cars. It truly seems almost magical. We hope this presentation has helped you gain a basic understanding of how neural networks work. And as mentioned, there's not enough detail here to be able to build and program your own networks yet, but we hope this has inspired you to go ahead and get that further learning and go ahead and learn how to build your own networks. We wish you happy coding.